I think I got it all worked out. If you didn't join the first part of this, oh my god, what a morning. What a morning it has been. I'm just going to move myself over a little bit. There we go. What a morning. I've literally lost most of the morning, if not pretty much most of the day, because it's getting up to 3 o'clock, to what seems to be an ill-fated update in our development environment. I rolled back to 1.5.1, version 1.5.1, and started a new project with the firmware version that comes with, and everything's behaving again. So, oh, Hesty, Micro, you got some splaining to do. Alright, let's get back on track. Now, where were we? Well, we were going to add in some basics like, I wonder if we can just copy the stuff we did. Actually, you know what? In my haste this morning, I think I've blown it all away anyway. Yeah, pretty sure I have. Anyway, so let's start again. But let's test as we go this time. Let's start a new folder under source called I2C mux, because remember we need to be able to set our I2C channel. So we'll add in a new source file here. I would be really happy to just get to the point where we have the controller able to read the frequency that's being produced by one of the oscillators. That'd be a huge milestone to get to. In fact, that is our milestone for today. Cone in the pool for today. I'm going to change this a little bit. I'm going to rename this to I2C underscore mux. So do it a little bit differently to last time, because then we don't have to have like a separate header for it. Anyway, thanks for coming back. Thanks for joining me again. Let's hope this one's a good one. For this, we're going to be borrowing code out of our test board that we did. Remember, that was the project that we did yesterday. Everything was great. And then today, not so good, Charlie. All right, there's our select channel method. So let's go ahead and borrow that. It's our own code, so it's not stealing. I2C mux select channel. I was thinking we should, it's rather than having the address in there. Screw it. Don't try and get complicated. Alright, go to this file here. Define I2C mux default address 0x70. Just wish there was a way we could default to that if one wasn't provided, but it's okay. We need to include I2C.h. We need to include main.h to get the error handler. Might do them in reverse order, hey. And interestingly, like, I moved away from I started using the STM development tools on a Linux VM because they were just so horrendously bad on the Mac. But version 1.5.1 so far seems okay on the Mac. I wasn't getting the horrendous performance issues I was getting before, so hoping that stays the same. Alright, so we can select a channel, but then we want to be able to scan the bus and see what we find. So let's create a new folder. I2C scan. And probably could have just put these under an I2C folder, would be better, but don't complicate things. You've started I2C scan .c, and again borrowing the scanner code we'd already written. That's not what I want. Is this it? Yeah. Scan I2C bus. Now, one cool thing that I did get working, it's not all frustration and loss today. I did get printf via the serial wire output working. It's pretty janky, it's not great, but it works. And it's a good reminder to next time include a serial UART so we can do serial debugging from day one. You lives and learns. Okay, this will operate the same. Yeah, that's exactly the same. We don't need to change anything there. So we'll just add this method into our I2C header. Let's just remark that this all comes from I2C mux.c. This is from I2C scan.c. And we're gonna need the HAL inclusion here. Or actually, oh, no, because that'll be a circular reference. Main.h will have it. Excuse me. So just need that HAL. Let's get back over here. Include that. Okie dokie. And then lastly, we just need the I2C mux select channel method. And let's put that in I2C.h. There we go. Cool. Now, is that build? Not quite. Be nice if that worked, but that'd be hoping for too much, wouldn't it? Clear that. Build that again. Right, so the I2CH is missing, or it can't find those I2C handler events. Now, that'll be because it's including the HAL, but the HAL is not yet enabled I2C. So let's go into our configuration here. Go to connectivity. Again, I'm going to start super minimal. We're just going to turn on one I2C peripheral. We're going to put it in fast mode. And we're going to disable the pull-ups in the GPIO section. No pull-up. No pull-up and pull-down. Save that. Now once we've saved that, it'll go and generate its boilerplate code, which should include the references in the HAL that are currently not building. So let's try again. There we go. Now I did see an implicit definition of printf in there, which will be in our scan. Let's fix that with an include standard IO. Build that. There we go. 0 error, 0 warning. Beautiful. But of course, we're not actually doing anything at the moment. But you know what? Before we get anywhere, let's just make sure our project is still sane and working. So let's build it. Let's run it on the board. So we're at the HAL init. Can we skip over the HAL init? Why aren't I in debug mode? Oh, this is fail whale already. Not total fail like it was before, it just hasn't flipped into the right view. Try that again. There we go. We're at the HAL. Well, the HAL init, and I can skip over that safely, and we should be in the while loop now, and if I break now, yeah, we're in the while loop. And we've even got systech working without enabling a timer. That new firmware has really broken the whole thing. Something must have changed in the timer system, I think, maybe? But, like, how does that get through quality assurance? Does no one test it? You know, looks good. Approved. Code reviewed. Right. Let's make it actually use that code we just added in. Let's scan our I2C bus, please. And we do that first by saying I2C channel select, I2C mux channel select And which bus are we using? We're just using bus 1. That's the only bus we've got configured because we're starting at minimal. I2C Mux default address, and we're selecting channel 0 because remember, when those power up, they're not selecting anything. I2C scan bus HI2C1. Now neither of those will work just yet. We've got to include I2C.h, that's our functions. Try and build this now. And we got undefined references to I2C Mux channel select and I2C scan bus. Well, that's odd because I've included the header. I2C Mux select channel. Oh, and this is a little bit different. This would be I2C scan bus. I2C Mux select channel. Just update our naming here of the functions. I2C scan bus. And what did we get wrong here? Nope, that's the wrong main, so let's close that out. I2C Mux select channel. Programming grammar. I try to have a pretty natural flow to the grammar of my function names and stuff. I don't try and get too hierarchical in the... You know, there's always a balance between the hierarchy of a function versus the just grammatical flow of it. Like I could have had I2C Mux channel select, because it's the I2C bus, it's the Mux, it is the channel, and you are selecting it. But I prefer a bit more a grammatical, like I2C Mux select channel. Just a personal taste. All right, so that, if we break now, is in its while loop. Lovely. And if we go to the scan, if we set a breakpoint here, when rerun, we should see if it's actually finding anything on the bus. Because remember, this is where it all went wrong big time this morning. When we tried to do this and we couldn't find anything on our bus, nothing was working, it was all horrible. Ah, frickin' finally, there we go. Look at that, things are being found on the bus. We've got a result at 53 decimal, which is 0x35. Now what's at 35? Number format. Hex. 0x35. I can't remember what's at 35. Oh, the lighting driver. Yes. We installed one of the lighting drivers. That's what that is. Then we've got 47, which is the broadcast address of the DAC. 48, which is the individual address of the DAC. 70, which is the MUX, and everything's there, everything is accountable, everything is talking to us. That's bloody awesome. But one thing that's a bit of a step forward for me in terms of this project now is I've actually set up, as I mentioned at the start, I set up printf via serial wire debug. So rather than having to break on stuff like that, we should now be able to run this. And before we step into the program, so remember it always starts off at that initial breakpoint. Here, we can go to our data console, serial wire viewer data console, begin a trace, and go. And look at that, we get debug messages saying found 1, 71, 72, 112. So that works, yes. And because of all the problems we had this morning, I am committing often and committing early. Added I2C channel select. Added I2C bus scan. Cool. Did that add the files? No, it didn't. There we go. Ah, what a relief. Okay, we're making progress finally. Now, what I said I really want to be able to do is to resurrect the old tuning code that we had that frequency counted the incoming signal from the analog oscillator to basically determine its frequency. So what frequency is it oscillating at? And that sounds great, but I can't quite remember how we did it. So we're going to take a look at this file here, DAC tuning. I opened the file and it disappeared on me. What the hell? Oh, right, because the project's gone missing. Oops. Yep, just remove that. What? Continue to force delete. Burn 1 nucleo contains resources that are not in sync with that. Oh, just go away. I don't know what it was whining about then. But what I do want to do, because I moved that project out of their way, so that's my own fault for doing that. Let's go find that, because we're going to need to look at the way we did this as a bit of a reference to remember. I know it's done with a timer, and I know it's done with a simple form of frequency counting. But that's about all I know. So there we go. That's our old project. That's when we were creating the firmware on the little Nucleo board. Now, where did that go? There it is. Core DAC. Where is it? Is it in the timer callback? DAC timer input capture callback. Yeah, okay. Yeah, here it is. Yeah, okay. I kind of remember this now. If it's the first value we've captured, we capture it and then we set that flag. Otherwise, if it's the first one that's captured, that's weird to have an if-else there, because... Anyway, we can tidy this up. This is obviously code that I hacked together very sloppily. And it doesn't actually look like my code. It's not the way I'd capitalize things. So I've obviously modified this from something else that I found. But if we haven't captured the first value, we capture that. Otherwise, it looks like we read the captured value from the timer. We calculate the difference in there. That deals with it wrapping. And then we get the frequency of our program clock. Okay. Sorry, peripheral clock. Okay. Yeah. All right. This shouldn't be too hard. Where shall we put this? What's a nicer way to format this code? Let's put it in... Well, where's our firmware gone? There it is. Core source. I guess tuning, right? Let's just create a new folder. New folder. Tuning. And I'm going to start a new file in here. And we'll call it tuning timer .c. Let's grab this and let's make this code a lot nicer than it is. Okay, because we've got a bunch of, we obviously keep these as static values to keep track of something. Which makes sense, that's our state. And we only ever listen to one oscillator at a time, so that's okay. But let's tidy this all up here, because we've got a mutually exclusive thing here. If first captured is 0, so if not is first captured, do that, else else we read the value. This deals with a wrapping. I actually think this wrapping might be utterly pointless because I'm pretty sure integer wrapping is handled gracefully in this runtime. Otherwise it's an error. Then we get our peripheral clock frequency. If we've got a difference to calculate to avoid div by 0, we do that. And then we reset back. Okay, that makes sense. Roughly makes sense. Gonna need to include main.h so we get the error handler there. But also this here can go straight into well, where should that go? This is like we're overriding a capture callback, so I'm gonna actually put that in our main. That's going to be the wrong main, isn't it? Is this the right main? No, this looks like the right main. If we go down to user code 4 here, yeah, this is sort of where we override some certain bits from the HAL, right? And this is where we've said basically, hey HAL, when we're using timer in capture mode, when this is a generic callback that happens, right? And if it happens that the channel is active channel 3, then we know that that's the DAC tuning oscillator, oscillator 1. Otherwise, if we know that it's channel 1, then it must be oscillator 2. Cool. And we just pass that straight on to our actual timing function, but we might want to rename that. Let's call it tuning timer input capture callback. And we're going to need a tuning.h. And then the tuning.h will, now I should have grabbed the whole, method. Okay. There we go. Now this will need to include the HAL. I'll remember this one day. There we go. And so that's our function that we call back to our main. Okay, now what I got to remember, so we're getting pretty close now to being able to do this frequency counting magic to be able to listen to the oscillator and hear what frequency it's oscillating at, which is the first step in being able to tune it, right? We've got to listen, then we've got to work out how to tune it. There's 2 oscillators on the board, well actually there's 3, but only 2 are tunable. And I siphon off a little triangle wave signal out of them and connect it to PE9 and PE11. So the next task is to configure those pins on the microprocessor to be set up to be a frequency counting timer, or a timer using capture mode. Okay, so PE, what did we say? PE6? PE9 and PE11, so close. Let's just do PE9 for now. PE9, where are you? There you are, PE9, timer 1, channel 1, brilliant. Now if we go to timers, timer 1, we're going to put ourselves in input capture direct mode. That's what I want. And I'll need to double check these settings, but I think we can just leave them as that for now. GPO, no pull up, no pull down, great. And just double checking our callback here, because remember we looked at the channel to determine whether it was oscillator 1 or oscillator 2. I think we need to change this a little bit. Oh, that was weird. Welcome to STM. You know what, let's just mark this out so we get it right. Oscillator 2 is connected to PE11. So what channel does PE11 show up as? PE11, there it is. Timer 1, channel 2. Well, that's kind of perfect, isn't it? So we go to timer 1, channel 2 is also input capture direct mode. Nice. that means we just make a little bit of a code change here in our file that says if we see a callback on timer channel 1, then we know it's oscillator 1. If we see a callback on channel 2, then we know it's channel 2. Easy, right? Where are these defined? Is this my own? I don't think it is. Tuning timer, channel. Let's just search. Where else is that used? Nope, it is. It's defined in the HAL. Okay, beautiful. We ready to build? What else have we got to do? Let's just check the parameters in this. So that looks fine to me, and but I'm going to save it, and then do you want unsafe files? Do you want to save unsafe file? Yes, always. We'll just take a quick look at the old project and make sure that we have the right prescaler and counter configuration, etc., etc. And that was in this little one. Boom. Nucleo? No. Oh, what? Okay. Well, you never migrate because that brings in the terrible new version that's busted. So we'll just download the firmware that this project was using so we can open it up. And then we'll be pretty close to seeing if we can register a frequency. And once we can get the frequency out of this, once we can tell what frequency the oscillator is moving at, then we're really cooking, right? Because then we can start modifying the voltage that's being applied to the control voltage port, as well as the resistance that's being applied to the scale tracking. And the combination of those two will allow us to calibrate and tune this oscillator. And that's going to be cool. So let's see how we did this. Remembering before, it was timer 4 channel 1 was the example. And I think it took me a while, I remember, and you might remember if you've been catching this stream for a long time. Took us a while to wrap our head around this and remember the right settings. So I'm going to just screenshot those, in particular that prescaler. Sounds familiar. And close that. Thank you very much. And we'll open this version of it. I do wish it was just a little bit faster. I mean, it is what it is. And let's go to timer 1, channel 1. Yeah, see, we need to set that prescaler, pretty sure. Let's grab that screenshot. Just replicate these settings. So prescaler of 102. Counting up 65535. No division. The rest of that I think it was just that prescaler, and we may have to monkey around with that a little bit as well. I'm not convinced that's actually the value we need, but we will soon find out. So save that. And the other little tricky thing in here was that the way that the tuning works is you kind of turn that timer on, listen to the values, turn it off, and then check your frequency value, right? So you need to let it run for a while to sort of normalize. Like if you look here, see this bit here where we say HAL timer start, HAL timer delay, and then stop. So, and why do we have, okay, yep. So let's go to our tuning timer function here. And we'll have a new method here. We're going to call it tuning timer enable or start. Probably need some parameters there. So that first resets the values, then yeah, so we're going to take DAC settling delay, I think, 1 second should be fine for now. Let's call this oscillator settling delay because it's not the DAC. Okay, it basically says we're going to listen for a second to try and determine what the frequency is that we're hearing. And then we're going to need a stop. Oh, well actually, it does that automatically, doesn't it? So let's be tricky and call this listen. And we could even, if we wanted to be really cool kids here, tuning timer listen. Let's call it tuning timer get frequency. Okay, so that's actually going to run, and we'll have it return the frequency that it's discovered. That's a nicer way to do it. And we'll put that in our tuning.h. And yeah, we should be able to now use this. Modulo fixing a couple of errors here. Timer channel undeclared. Okay. And just call it channel. Build this. 0 error, 0 warnings. Nice. So at the moment we're oscillating at about 296 hertz on oscillator 1. So in our main, let's go to our main and let's just try it out. This is exciting. I'm excited, especially after the morning. That was not a fun morning. It was not a good morning. UNT32T, I should say. UNT32T frequency equals that, and we're going to be talking to, well, I think it's just H time 1 and timer channel 1. Wonder if we've lucked those variables right first go. And because we've now got printf set up, I'm going to printf frequency. Let's be kind. OSC1 frequency is an integer. All right. Wow, is that it? Is this going to work? Build this. It wants an int. Okay, no, right. So you want an unsigned long, I'd imagine. UL. That was pretty naive of me using %i. %u expects unsigned int. long unsigned int. Wow. Is it that? Yes. All right, and now we just need to include the timer.h. So include timer.h, or stop. Close that. Okay. Include tuning.h. Build successfully. Come on. Yeah, 0 error, 0 warnings. Let's go. And let's just see, what are we actually oscillating at? 296, if you can see on the oscillator there, on the oscilloscope there. That's that yellow line. Okay. Yeah, pretty sure, yes, it does have standard int. Yep. Yeah, because that's where we get the UNT32T and all that sort of stuff. So let's turn on our serial tracing. I wish I could always turn that on. Run it. Okay, so the bus scan worked, but our frequency, interestingly, has come back as 0. Haha. That can't be right. So, what could it be? Let's go into our tuning timer here. Do we need to let it run for longer? Let's set a breakpoint and watch this go. And let's also make sure we're seeing our breakpoints fire. So let's go again. Yeah, I do love me some very descriptive integer types. Okay, so timer. We're starting the timer. Ah, but we're not getting any callbacks. Okay, so I'm guessing we probably need to stop this, go into our configuration. We probably just haven't turned on an option to say, hey, I want an interrupt to fire whenever that timer captures a value. Pretty sure basically how this works is the timer is oscillating at a very predictable frequency, which will be that system peripheral clock modulo or divided by the prescaler, I guess. It's oscillating at that frequency, and each time it oscillates and our analog oscillator happens to also be at a high signal, I think that's when it counts and says, yep, okay, that's a capture, and it fires the interrupt. And so, you know, you get sort of the interleaving of that, and it's, as long as you've got your timer running fast enough, you can frequency count. Now, here we go. Yes, break interrupt, nope. Timer 1 update interrupt, nope. Timer 1, Timer 1 capture compare interrupt. Yes, I think that's what we need. Okay, let's see. Let's run it. See if we can. Let's see if we actually get an interrupt firing from the timer saying, I see the signal. Okay, we're running. We're turning it on. Yes, we're getting callbacks. Now I'm going to turn that off because that's going to totally upset the result. And that's all good and well, but I forgot to turn on serial debugging, so we'll just need another breakpoint to see what frequency did we count. Got to find a better way to do serial output. Okay, here we go. So start listening, and it listened, and the result is 30534. Well, it's not far off. Oscilloscope saying... Oscilloscope says about 296, and we've counted 305, so a little bit of a worry that there's that discrepancy, but I'm not going to kick it out of bed for just this this initial result. I think what we need to work out though is this prescaler value, and we also need to first of all commit our code. So let's git commit, or git status, git add git commit am added frequency counting timer code. All right, now we're assuming that right now we are doing a pretty close approximation to actually counting the frequency of how the analog oscillator is performing. That's cool. It's like our board now has ears. It can hear what note the oscillator is playing. I want to see what happens though when we now go to a more advanced clocking setup. So when we actually start using our high-speed external oscillator, what happens? Let's just do this step by step and make sure nothing breaks. I'm just super nervous about this. Okay, let's run. Run and done. Okay. Let it listen, and it listened, and it returned a result of Come on. Are you gonna give me the result? Normally if I hover over that, it will expand it out for me, but it's not gonna do that. That's annoying. That's okay though. We'll just breakpoint here instead. Let it skip through to the next one, and that's 304. Okay, cool. So predictable results still. Let's now... All we did here was just enabled the fact that we've got an external oscillator. We're not actually using it. So now let's use it. Our external oscillator oscillates at 16 megahertz, and I would like to use that oscillator for the PLL input and the clock mux. So that's not actually going to change the actual clocking of any of our peripherals. We're just switching now to our external oscillator. Save that. And you know what, I'm going to... Actually, let's make sure it all works first. If this still works, then we'll check in our code at this point before we up the clocking speed. Okay, no errors, no warnings. Good, good. And we still look good here. We've counted a frequency. The frequency we counted, 304. Nice. Just to make sure we haven't gone off into the weird land we were seeing before, I can still breakpoint here and I get a sensible backtrace. I don't get off in these weird hex numbers I was getting with that stupid version before. All right, that's pretty good. Let's check this in. Oops. What do we want to say here? Enabled HSE crystal. And now let's go hog wild. Let's shoot for a maximum clock of 168 megahertz. Go, go, go. Bang. Except we just got to tell it to use the high-speed external for the PLL. And the system clock is coming out of the PLL. Nice, 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 nice. Now we're really cooking with gas. We've gone from driving our CPU at 16 megahertz to driving it at 168 megahertz. That I think is probably going to affect our frequency counter, or at least we might need to rethink that prescaler value. It's all a bit hokey pokey math that we'll need to sit down with a pen and paper and work out. It's just because the speed or the frequency at which that timer is running will affect what the upper and lower bounds of the actual audio frequencies are that you can count. That's why we need to care. But let's just see what this does. Remember, we were getting predictable results in the 300s before. And yeah, so it's thrown it right off. So our frequency is now coming back at 76, or actually, yeah, 76. And I can tell you for sure that we are not oscillating at 76. So what happens now when if we go into the timer configuration and we go into the parameters, we're going to need to prescale this way more. So let's actually do 256. And you know, we could probably mathematically work this out, but let's just try a little bit of trial and error first and see what happens. Alright, come on. Remember, we've got a hard stop at 4 o'clock, which is 21 minutes away. Let's see if we can get this prescaler value right. And if we wanted to cheat, we could always go and look at the system clock of the other board that we borrowed this code from and just extrapolate from there. But from memory, this was a case of just playing with numbers until we found something that got us roughly what was showing on the oscilloscope. So we're getting closer. So I would say if we go back in here, let's stop this. Go back in here. 350. It's just going to be total experimentation here. And then we'll fiddle with the DAC value to increase the frequency. So we send a higher control voltage to the oscillator and just see if we can actually count, you know, reliably up and down the spectrum of audio range. You know, we can take a few of these breakpoints off. We really only need to know what it counted, and what it counted was 259. Hey, that's close. It's at 296. All right. Getting very close here. Let's just up this to 360. Because we basically want to find the prescaler value that results in this counting something that matches what the frequency is on the oscilloscope, which is 296 Hertz at the moment, just as an initial reference point. We'll definitely need to tune this as we go. Okay, what do we get? 265. All right, so I think what we should do, let me go for 400. Come on, there is an ST link. You can find it. Here goes. Hey, Jada Spaghetti. Ah, it's going better than the morning. The morning was horrendous. Yesterday we had a great day writing test firmware for this, just testing out various bits and pieces on the board. Updated our toolchain overnight, and everything went to hell in a handbasket this morning. But now we're doing better. We're actually getting results we'd expect. Oh, that's damn close. I think that's nailed it. Let's go with that. This is reporting a frequency of 296. And that's basically what is being shown on the oscillator. I think it's probably closer to about, the oscilloscope I should say, I think it's closer to 295, but we'll roll with this for now. Now what I want to do though is I want to see if we up the frequency, if we make that oscillator go faster, does it, can it count accordingly? So just give me a sec, I'm going to use the trusty screwdriver tool here to up the frequency. Watch that yellow line on the oscilloscope. All right, now we're at about 1.47 kilohertz. Let's count. Well, let's let our board have a listen. See if it can hear that frequency. Okay, so it's had a listen and it hears, oh yes, 1.532 kilohertz. That's pretty much bang on. It is hovering around 1.52. Yeah! We got something that can listen. Our synthesizer has ears. Let's up the frequency way up. All right, we're at a hefty 10 kilohertz now. Let's see. The other thing we'll need to do is see how low can it count, because we need both. We basically need a couple of octave range to test and calibrate this. So this is at 10 kilohertz and it heard, yes, it heard 10 kilohertz. Let's turn it way down. Okay, that's at 107 hertz now. Any lower, I'm going to have to adjust the oscilloscope settings. How's coding in C? It's good. I like doing embedded C stuff just because it really gets you back to nature. Gets you back to working with the bare hardware. There's no malloc here, there's nothing fancy, there's no threads. It's just one core doing what you tell it with the memory that you've given it. And I like that. Okay, what did here? What are we at? We're at 110 hertz or so. It's exactly 110 hertz is what it heard. This is bloody awesome. Let's adjust the oscilloscope a little. Okay, we're at 19.8 hertz, so we're like subaudible at this point. And let's see if we can hear. I will answer your question in just a second, JDS Spaghetti, because that's a good one. Okay, what did we hear? We're oscillating at about 20 hertz now. 20 hertz. I'm beyond happy. This has redeemed the day. Let's check this in. Frequency counting at 168 megahertz. Clock speed. Tested 20 hertz to 10k hertz. Bang. That's our achievement for the day unlocked. JD Spaghetti, look, the topic of this comes up quite often. And we even have a little keyboard shortcut for it here, so I'm just going to type that in. Oh, okay, maybe it's get started. There we go. Little blog article that I wrote. The thing for me is like, it depends what you want to do, what you want to achieve, right? So think of a problem you want to solve, or think of a challenge, or think of something you could do to get started, whether it's like, I wish there was an app that did this, or I wish I could write a script that did that, or I would love to know how to do this. And then use that as your guide, right? Use that as your North Star, your beacon, your I don't know, metaphor that I've lost. Use that as like your thing that you focus on, and just learn enough to get that done, right? Because that takes away the whole, what language should I use? What language is important? And don't, whatever you do not get caught up in this horseshit of, this language is not popular, I'm not going to be able to get a job in that. Oh, this has lots of Google searches, I'm going to pick that language. That's noise, right? That's noise. What's important is you learn how to solve problems, right? That is the key to all of this, right? And whether you do that with a shell script, whether you do it with JavaScript, whether you do it with embedded C, Swift, hell, do it in PHP if you've got to. But just get started, right? Pick a problem, think about something you want to learn, or a way you'd like to approach that problem, and just have at it. And then what you learn from that will help guide your next set of exploration. But if you just want a simpler answer and are like, that's great, old man, but like, just get off my lawn, right? Tell me what I can do. I like starting off with JavaScript just because it is so malleable in terms of, you can learn JavaScript and write some front-end stuff, like for a web app. You can write JavaScript to make a native app with React Native. You can write JavaScript to do back-end stuff with Node.js. You can write old-school web pages with JavaScript. You can, if you can write JavaScript, you can do just about anything these days. So it's a great place to start in terms of learning, getting that foothold into a language that allows you to experiment with lots of different stuff. So hopefully that's helpful for you. Now, we got 11 minutes left on this stream. Trying to think of the best thing for us to do here. I guess we could start sketching out our tuning code here, because it's, now we can listen, now we've got ears. But that's only half the battle. We need to manipulate it. So let's create a new file. We'll call it tuning. Oops, no. We've got to create a new C file. and call it tuning.c. Right. Include tuning.h. Include main.h. My watch is telling me it's time to get up. Void. Right. What is this function going to be called? We're going to call it tune. Well, I really just want it to tune. Let's just tuning. I don't know. I want it to be like just go. Hey man, thanks for the follow. Let me just fix the music here. Why does this happen? Why does it still happen? Every time the first follower in the stream breaks the music. Every time. I'm the only streamer in the universe that this seems to happen to. Two of the hardest things in computer science: cache invalidation or syncing, and naming things. Because I've gotten this file called tuning, but I really just want tuning. This is ugly. Tune oscillator. That's gross, but it'll do for now. Or actually no. No, because yeah, it's a little bit different. Because first we've got to say tuning, calibrate, scale, and to do that, we're gonna need. Oof, what are we gonna need? We're gonna need a few things passed into us. So let's just we just snip that off like that for the moment, and let's just think about what this has got to do. So the way in which we calibrate the scaling. So you know, think of a keyboard, right? Keyboard has lots of keys. Musically, we've got octaves. You know, octaves got 12 notes in it, 12 steps, I should say. The frequency between each octave, so each grouping of 12 steps, is exactly double the frequency. So if you've got, you know, A4 is 440 hertz, A5 will be 880 hertz, right? That's how this works. But there's two elements to making an oscillator actually work musically. First of all, it's got to be tuned. So you've got to know that when you send it 2 volts, it produces, you know, A2, for example, or A5, right? You've got to have a predictable relationship of knowing you send it this voltage and it produces this frequency. With a lot of oscillators, though, there's so many challenges to overcome, right? There's temperature variances, there is variances that happen across different scales, there's the non-linearity of response, all that stuff. But we don't have to worry about that because we're using a glorious oscillator from the 1980s called the Curtis Electromusic 3340, or the SEM 3340. And this chip does a lot of that stuff for us, right? It does its built-in temperature constant, does the built-in temperature compensation. It's already set up to do a linear volt per octave scaling, but it needs two things. It needs a calibrated voltage per octave sent to it. So 1 volt is 1 octave, 2 volts is the same note but 1 octave up. And that's fine, we can do that. The tricky bit is there's a variable resistance or a variable amount of current that you send it on one pin, which helps it understand how to achieve that scaling of, you know, voltage. You know, 1 volt is this note, voltage, or 2 volts is that same note but the next octave up, and that's what we've got to calibrate first. So the first thing in this tuning, and it's going to be a delightfully recursive process actually, because what we're actually trying to determine is we're trying to determine the correct digital potentiometer, basically the resistance, trying to determine the correct depot value for the scaling between a 1 volt variance in CV to produce exactly double the frequency. E.g, if we send CV of 1 volt equals, well, let's do 3 volts equals 440 hertz, A4, then CV of 4 volts equals 80 hertz, right? That's the result we're trying to get to. And the way we will do this is we're going to use a recursive function that calls itself, where we'll say tuning dpot value for one octave tracking. And there's going to be a bunch of parameters that we've supplied to this. But this is the sketch, this is the outline. And so our end goal here is to determine what is the 8-bit value wherein we achieve the expected scaling across. We're going to have to give it like the SPI bus. And we're going to start it off by saying, you know, so SPI bus, we'll have to get that in somehow. But we're going to give it a minimum. We're going to say start, you can go from 0 to 255 is your range of values. And we would like you to calibrate to 440 hertz. I think that's roughly what we'll say. Yeah, let's do 440. You know, the 440 works. Now, this is going to be recursive. So it's going to take that SPI bus that we'll have to work out in a sec. It's going to take its uint8 min value, because the digital potentiometer is an 8-bit device, right? You can send it a value between 0 and 255, 256 individual values. Frequency. And so the first thing this needs to do is we need to set DAC value to achieve desired frequency. So that's going to be almost its own little call out to the DAC to do a binary search through its address range to find, you know, if I send you 2.6 volts, that achieves frequency 440. Great. I'll take that voltage value from you, set the dpot to something, and then double that voltage value, listen back and see if I hear exactly double, because if I do, then I'm calibrated. If not, I need to continue this search. But actually, just thinking about it, the first thing we need to do is set dpot to halfway between min and max, right? Because this is a binary search. Then set the DAC to achieve the desired frequency. Set DAC value to voltage times 2. Listen to achieved frequency. And this is where the magic of recursion comes in. And this is just like bad pseudocode at the moment. If actual frequency is higher than frequency times 2, so we got a note that's higher, what we would actually do is then call ourselves again, same bus, but this time the minimum value stays the same. The maximum value though will be our dpot value we used this time, and the same reference frequency. Otherwise, if the frequency, or let's just keep this simple. Else if actual is less than frequency times 2, right? So we've got a result that's lower than expected. We'd go the other way. We'd recursively call ourselves, but this time we'd say, well, we've found this minimum value that's already producing something too low, so don't go any lower than this. Run our binary search again, using the value we just tried as the minimum, but restore our same max value. Otherwise, you assume you actually nailed it and you got a frequency that's equal to that. And, or actually, you know what, maybe we'll do this. Else, if we've reached the point where there basically is nowhere else to go. So what would that look like? We basically would have achieved the point where there is nowhere. Actually, look, let's keep it simple for now. That's an implementation detail. Otherwise, we assume success. We've actually found our value that calibrates accordingly. All right, I got to run because it's 4 o'clock, but this is the basics of how this will work. All right, this is the beauty of recursion. We do the same thing with tuning the oscillator, right? It's just a simple binary search. You say, here's your minimum, here's your maximum value. Somewhere in that haystack is a value that perfectly produces the result we want. So start in the middle. Does that produce the result we want? No. Does it produce a result that's higher? Ah, okay. Well, in that case, search the lower half of that haystack. Search the middle of that. Does that produce what we want? No, it produces something lower. Aha. So it's not going to be a lower value. It's going to be somewhere in the middle of that, right? You just keep narrowing this down until you hit upon the right value. It's beautiful and it works. And I know it works because I wrote the same code for the just a simple oscillator tuning, but this is new for doing the actual scale tracking tuning. But folks, I gotta go. And thank you so much for being here when we resurrected my faith in this platform. Because boy, I was seriously doubting what we were gonna do this morning when nothing was working. We'll be back tomorrow. We got a whole lot. Yeah, exactly. O log n for the win. I love that big O notation. We will be back tomorrow to continue this journey, and I'll see you folks